Hello everyone. Today my topic is parallel reactions. In our previous two videos, we have already studied the kinetics of complex reactions, of opposing reactions. So, what are the kinetics? Now, interpretation of velocity data of many reactions becomes very difficult due to the occurrence of several reactions which take place simultaneously along with the main reactions. So, to study them in detail, we need carefully planned experiments to study the influence of products and reactants. Now, important reactions in this category are opposing reactions, of which two videos I have already made. Do watch them for a better connectivity. The next one is parallel reactions, consecutive reactions apart from chain reactions, which I'll be making in my upcoming videos. So today the topic is parallel reactions. When a reactant A undergoes two or more independent reactions at the same time, it is considered a case of parallel reactions. Each independent reaction gives rise to its own set of products. Let us consider a reaction A, where A is the reactant which undergoes two reactions. First, this is 1 and 2 to form B and C. Let us assume this to be reaction 1 and this to be reaction 2. Now, before going in detail, let us take an example of parallel reaction. That is when ethyl alcohol reaction, it takes place in 3 steps. The first, it may form C2H4 and water. The second, in which it may form an aldehyde, ethanol along with hydrogen, or it may form an ether along with water. So, under different conditions, ethyl alcohol, it forms different products. Let us consider this general equation, general parallel equation. Here, K1 at K1B is formed, at K2 C is formed. Now suppose A is the initial concentration of the reactant A. Let X concentration of A decomposes in time t to form partly as B and partly as C. So if Y and Z are the amounts of B and C in time t, then rate of disappearance, or you can say rate of appearance, rate of disappearance of A is equal to, it is x, therefore it will be dx by dt. This is disappearing and this is forming. Therefore, rate of formation of B and C together, that will be, this will increase, that will be dx by dt. Now, separately, when we speak about the rate of formation of B and C, formation of only B, then we can say dy by dt. Since it is forming, we are using the positive symbol. And formation of C, we can say dz by dt. As both B and C are formed from A, we can write dx this is equal to this and this. Dx by dt is equal to dy by dt plus dz by dt. Now, once we have reached here, we can assume, or if we assume that the formation of B from A and also formation of B from A and also formation of C from A are first order reactions. The velocity for formation of B from A can be given as dy by dt is equal to k1 A minus x. Similarly, velocity for formation of C from A can be given as dz by dt is equal to k2A minus x. We have got the values of dy and dz. We will substitute these two values in this equation, that is dx by dt. On substituting, dx by dt is equal to k1 a minus x plus k2 a minus x. On solving this, what we get is, or taking out a minus x as common, we will get k1 plus k2. Or when we bring this term on this side, we can say it is dx by a minus x is equal to k1 plus k2 dt. k1 plus k2 dt is nothing but k dt. So we can say dx by a minus x is equal to k dt. That is k1 plus k2 when it is considered as k. Like in our opposing reaction, k1 plus k2 is equal to k. Now integrating this, what we get is, on integrating, what we get is k is equal to 1 by t, this will go here, ln of a divided by a minus x. So the value of k can be obtained by recording the concentration of A with the time t. But amount of B at any stage divided by amount divided by amount of C at the same stage is equal to K1 A minus X divided by K2 A minus X. Or we can say, when this gets cancelled out, it is K1 by K2. Or we can also say that it is equal to K dash. So the estimations of B and C at the end of the reaction give the value of K dash. So the values of K1 and K2 can be evaluated separately from experimentally determined values of K dash and K. That is, K1 plus K2 is equal to K. We have done it here. And K1 divided by K2 is equal to K dash. That is, we have found it here. So we can say that K1 is equal to K2 K dash from this equation. K1 by K2 is equal to K dash. We can say K1 is equal to K2 K dash. Therefore, K2 K dash plus K2, that is, I'll just take another pen. Value of this we will substitute in this equation. Then we get K2 K dash plus K2 is equal to K. Take this out common. K2 will be equal to K dash plus 1 is equal to K. Or keep this in one side and you can write it K2 is equal to K divided by K dash plus 1. Now substitute the value of K2. Then we get K1 is equal to K dash divided by K dash plus 1. Now Weysider, a scientist, W-E-I-G-H, I'm sorry, W-E-G-H-S-C-H So Weysider's test is useful to distinguish the parallel reactions from opposing or consecutive reactions. Now this test states that the ratio of amount of substances formed in parallel reactions is independent of time, provided that the order of both the reactions is the same. So that's it for today. I'll continue in my next video, consecutive reactions. Do keep watching. Thank you.